will now focus our attention on question 4. And you should realize that question 4 will actually look at a geometric sequence or series, because already we covered the two other sequences and series, which is quadratic sequencing and arithmetic sequence or series. Now, in this question, we have the following information here. Fractal geometry is used to design Sierpinski triangle. Now, fractal geometry is a branch of mathematics which looks at diagrams or geometric figures that have the same degree of regularity. That means that if you zoom or magnify those diagrams at different levels, you see the same patterns. There's some form of self-similarity. And we usually say that a small part looks like the whole. If you deal with such geometric figures, they fall under a branch of mathematics called fractal geometry. Now here we use fractal geometry to actually design what we call Sierpinski triangle. Now a Sierpinski triangle is named after a great Polish mathematician called Wacław Sierpinski. He was a very interesting character. Now the question continues to go further and say that the first triangle consists of one large equilateral triangle. So if we look at our first triangle, which is here, the first triangle, it has a one large equilateral triangle. To say this is an equilateral triangle means that all the three sides are the same in length. So that's what we have in the first triangle. Then the second triangle, so this was the first triangle. Now the second equilateral triangle is formed by connecting the midpoints of each side of the first equilateral triangle. Now what do we do here? If we take the first triangle and we connect the midpoints of each side of this first equilateral triangle. So in this equilateral triangle, I take this side here and connect it by a line that will make these two sides to be the same, the midpoints like that, and also this one so that it has the midpoints like that. So I cut this triangle so that this side and this side is the same, and this side and this side is the same. And I also cut this length here so that this side and this side is the same, and I also draw another line so that this side and this side is the same. Then I'll be able to produce this triangle here. This is how we get to the second triangle. Now, if you look at then the second triangle, you will notice that we have one large equilateral triangle as we used to have here, because really we formed it from the previous triangle. But then I start having a couple of triangles inside there that are upward facing, and also one triangle that is downward facing. So that's what we have in the second triangle. They then say now here that the third equilateral triangle is formed by connecting the midpoints again of the sides of the three small upward facing triangles. Now, if we focus on the upward facing triangles, do you see these upward facing triangles? And I repeat the same pattern where I'm going to cut this triangle so that this side and this side is the same, and cut this triangle so that this side and this side is the same, and this side and also in this side is the same by cutting here. And I do the same, with all these upward facing triangles, all the sides to be the same here, and all the sides to be the same. I then form the third triangle. That will lead me to the third triangle. This is how we got to these triangles that are here. And again, you will notice that when you do this, you then have upward, we actually have the original equilateral triangle, right, that we started with the big, large equilateral triangle. Then we still see the upward facing triangles like that. We have the upward facing triangles emerging there like that. And on this pattern, we then have the downward facing triangle as well that will be part of that triangle. Now, they say here that an infinite number of equilateral triangles is formed by continuing to use line segments to connect midpoints of each side of the sides of each upward pointing equilateral triangle as shown in the diagram below. So what they mean here is that we continue doing the same pattern, cutting these triangles, so that the upward facing ones, so that we cut the midpoints like that, we cut the midpoints like that in all these triangles. We then are going to form this triangle, and we're also going to form this triangle if we continue doing the same recurring pattern. So, and eventually we'll form an infinite number of triangles, meaning a large number of triangles, if we continue to triangle 6, triangle 7, and so on and so forth. That's how the pattern is being formed here. But the interesting thing here that I want to talk about, going back to the term fractal geometry, is that if you look at this triangle here, that's what we call a Sierpinski triangle, and it's formed using fractal geometry. In other words, if we zoom this triangle, you will see that the small part here is the same as the whole, is the same as this big part. And if you look at the big triangle, it also has the same pattern. There will be upward facing triangles and downward facing triangles. So the pattern repeats itself even at a lower level when you zoom in and also when you zoom out. You see the same pattern if you zoom into a small piece like that. You'll see that there will be 3 upward facing triangles and 1 small downward facing triangle. And if you look at the bigger triangle, you would see that we have upward facing triangles and a small downward facing triangle. That's what we call fractal geometry. Now obviously this here will be linked to geometric sequences and series, but let's see how that comes into play. They say here that, and one thing also that I could also add here or share, is that all these triangles, when you do a Sierpinski triangles, even the small ones inside here, they are actually equilateral triangles. That's why we can repeat the same pattern until we get to a lower level. All of them are equilateral triangles. Even the small ones here, they all have the same equal sides. We see the same recurring pattern at the bigger level, and also when we zoom in at the lower level. Now the question continues to say that the upward pointing triangles are used to form a geometric progression. So they tell us that they use the upward facing triangles to form a geometric progression, meaning a geometric sequence. So here, if you look at this is an upward facing triangle. We use this to form a geometric sequence. We also use this large triangle and also use this small upward facing triangles to form a geometric sequence. The same thing here, we're going to use this large upward facing equilateral triangle and also use this small upward facing equilateral triangles to form a geometric sequence. So this is very important to notice, because what we're saying here is that we don't use the downward facing triangles to form the sequence. We focus on upward facing triangles to form our geometric progression or sequence. This is a very important statement. So even when you construct the sequence, you must focus on the upward facing triangles. Now they further say here that each term of this progression is formed from the ratio of a large to small upward pointing equilateral triangles. Now what are they saying here is that if we want to find the terms in this sequence, we are going to use the ratio of the large to the small. Remember, a ratio is written as a number of A is to B. So if I say 1 is to 2, or if I say 2 is to 4, that's how we use our ratios. Now in this case, we're saying this will be a large triangle divided by a small triangle. Remember, a ratio means division, so this can be written as 1 over 2, this can be written as 2 over 4. That's another way in which you can write ratios. So here it means our terms would be a large triangle divided by a small equilateral triangle, and all of them should be upward facing, remember, because we are forming them from the upward facing triangle. Now the question continues to go further to say the first term of this progression is a large upward pointing triangle, which is given by T1 is equals to A. So now what are we saying? We're saying when we want our first term, T1 would be an A and will be given by 1. So meaning our first term, we simply just take this large upward facing triangle and we form our first term. So that means here, if we want our second term, we're going to take the large equilateral triangle, which is this triangle here, and we are going to divide by the small upward facing triangle, and you have 1, 2, 3 of them there. So this is going to be 1 over 3. I'll do the same if I want the third triangle. I'm going to take the large equilateral triangle, which is this, and divide by the upward facing triangles. I can see I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this means I'm going to divide by a 9. Already you can see that there's an emerging geometric progression or sequence that is happening there. Remember, we are always taking the ratio of a large to a small. That's why I'm always dividing by a large triangle, which is 1, and 3 of the small ones. A large triangle, which is 1, by the 9 that are in there, that are upward facing, the small upward facing triangles. But from here, you can already see that we have a geometric progression. You really don't have to count these ones because they're a lot, or count these ones because they're a lot. You can already construct or see the common ratio there. Right, so that's what we have so far in terms of reading and understanding our question. And of question 4.1, they then say to us that write down the first 5 terms of the geometric progression. So I'm doing question 4 here, and I'm under 4.1. They want us to write the first 4 terms. We said our first term would be 1, our second term would be 1 over the 3, and our third term would be 1 over a 9. Already you can see here that our common ratio is 1 over 3. I'm multiplying by 1 over 3 to get to the next term, because if you say 1 times 1 over 3, it will give you 1 over 3. And then if I continue doing that, because remember, this is a geometric progression, they've told us, I'm going to multiply the 1 over 3 by the 1 over 3, and that should give me 1 over 9. So this means here, to get the third term, I'm going to multiply by the same constant or common ratio, where I'm going to multiply the 1 and the 1, it will give me a 1 here, and the 9 times a 3, it should give me a 27. And I'm going to do that to get the fifth term, which is where we should end. It will be 1 over 81. And those are the first 5 terms of this geometric progression. And really, you can see that our R here is a constant 1 over 3, just by studying this first 3 terms that we really have on these diagrams. You can see the pattern. You can confirm this really by counting these triangles, by saying 1 divide by, you count the small ones, there you'll get the same progression. But sometimes you need to see these patterns so that we can save time, because counting them can take a lot of time. So this is just 1 mark really, because there isn't much that you're doing here. You should be able to spend a minute to construct this pattern. So here we'll have 1 mark. And if we continue to question 4.2, they then say to us, write down the general term of this geometric progression. Already we know that this is a geometric progression, and we can see from this progression that our first term A is equals to 1. We talked about that, and our common ratio is 1 over 3. So that means I can use the general formula of a geometric progression that says Tn is equals to A r to the power n minus 1. This formula is there on the formula sheet. If you happen to forget it or you don't know about it, just check it on the geometric progression. But be sure that you know that this is a geometric progression formula, so that you don't use a wrong formula here. Now at this stage, I'm going to say my first term is a 1, and my common ratio is 1 over 3 to the power n minus 1, and this will simplify down to Tn is equals to 1 over 3, and we're going to have n minus 1. And again, if you look at this question, is only 1 mark really, because we're not doing any simplification, we're just substituting in the equation, and there isn't much simplification because we just have a 1 there. Question 4.3, we are requested to calculate the sum of the first 20 terms. So that means now we are turning our sequencing into a series. So that means I'm going to have a 1 plus 1 over 3 plus 1 over 9 plus 1 over 27 plus 1 over 81 and so on, plus so on, because now we're going to push this until we are at the 20th term somewhere there. Now to get this sum, there are actually 2 formulae that you can use. But the one that I'm going to use here is the one that works when our r is actually less than 1. So it's going to be Sn is equals to a open bracket 1 minus r to the power n all over 1 minus r. This formula would work when r is not equals to 1, when r is not equals to 1, and also when our r is actually less than 1, meaning is any number less than 1. And if you check our r here, it is indeed less than 1 because it's a 1 over 3, which is like 0 point something there. Now from here, this becomes a really substitution problem where we're going to say the first term is a 1, and here I'm going to have a 1 minus 1 over 3 to the power 20 because we're looking at the sum of the first 20 terms all over 1 minus 1 over 3. And now this question from this point on becomes really boring, because what we're going to do here is that we're going to use a calculator to then find our answer to this. Okay, what is my calculator doing there? So we're just going to punch the whole numbers as they are on our calculator, and you know, really this will then reduce down to give us an answer of 1.49. So the sum of 20 terms, remember this will be the sum of 20 terms, will be 1.49. That's what we're going to get as our answer there. It is possible for one to use this equation here that says a r to the power n minus 1 over r minus 1. You should get the same answer, especially because you guys, you use a calculator. So it should be able to give you the same answer. It's just that this one is preferred when our r is less than 1, as I said. But it will give you the same answer, like really the same formula. Now, if we look at this question, it is marked out of 2 marks. So here they only mark the substitution. So if you have the correct substitution and you have the correct final answer, because really this formula is there on the formula sheet the way it is. They don't really award you for taking what is on the formula sheet. Now question 4.4 says to us that is this series convergent or divergent? Explain your answer. Now before we move to answering this question, it's important to then revise what does a divergent and a convergent series mean. Now when we say a series is convergent, you know, the term converge means we're coming closer to each other, we're coming closer, we converge, we're going to a common point, if I can put it that way. And divergent would mean that we are moving away, you know, from each other, we're moving away from a common point, if you can understand it that way. Now in terms of series, what it means is that if you have a series, let's say you have a series here, I'll just use a generic series where I'm saying you have T1 plus T2 plus T3 plus T4, and we're adding, you know, a large number of these terms. But let's say when I add these two, perhaps I get A3, and when I add them, I add term 3 on this one, I then get 3.5. Then if I add term 4, I then get 3.5. Then if I add term 5, I then get 3.5. Then as I continue adding them, maybe I add the first 20 terms, I get 3.5. Then I continue adding the 50 terms, I get 3.5. Let's say I add the first 100 terms, I still get 3.5. Then it means this series is converging, is going closer and closer to 3.5 the more we add terms. And this would happen if our r is less than, is between -1. If our r is between -1 and 1, the series will converge. Our series will add up to a specific number. But a divergent series is a type of a series where if I add term 1 and 2, let's say I get a 3. But if I add term 3 there, I then start getting, let's say, a 5. Then if I add term 4, let's say I get a 8. Then if I include term 6 there, let's say I get a 10. Then if I include maybe term 10 there, I start getting a 20. Do you see that the more I add my terms, I'm actually getting a bigger number. my numbers are not going towards a common or point or a common number. They're getting bigger and bigger. We're saying that series is diverging. So that's the difference between divergent and convergent. So here, if you look at this series, what we actually have here, we are having a series that is actually converging. And the reason why this series is converging is because we said a convergent series is convergent. You will see it when your R is between -1 and 1. So here I'm going to justify this by saying since R is equals to 1 over 3, what this means, that is our R is between -1 and 1. That's why this series is converging. So if you put the R here, 1 over 3, you would see that is a number that is between 1 and -1. And so as you add the terms in this series, as we add these terms here, you can try this with your calculator. As you add these terms, you will see that you are going towards a common point. So if I add term 1 and term 2, I'll go towards a common point. If I include this, I'll go towards more or less the same number. If I include that term, I'll go towards a common number. And as you continue, you'll see that you are going to actually go towards a common point. And you would see that your number would be closer and closer to 1.5. It will always be closer and closer to 1.5. It won't be bigger than 1.5. That's what it really means here. Then this question really is worth 2 marks. I mean, this is obvious where the marks will come from. The fact that you were able to see that it's a convergent series and also your reasoning around that. Now, if we go to the last question, it says to us that calculate the sum to infinity. The sum to infinity of this series if it exists. Now, I can tell you now already that the sum to infinity exists for this series because the sum to infinity exists when R is actually between -1 and 1. And we know that our R here is 1 over 3. So the series here exists. In other words, this series converges. And the sum of infinity really, what it does or what we're calculating here, we're trying to get a number that the series converges to, the number that is getting closer to as we add our terms. That's what it means here. So we all know by now that the sum to infinity is given by S infinity all over 1 minus, not a plus there, it's a 1 minus R. And we said that our first term is 1. We have 1 minus 1 over 3 because this is our common ratio here is going to be 1 over 3. And from here, this question becomes very, 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 very boring because you're really going to use a calculator to get your final answer. So now here you will see that this series converges to 1.5. So the more we add terms, the more we're going closer and closer to 1.5. And really you can see this from the previous one because we actually have 1.49 when we add the first 20 terms. So you can see that when we add the next 30 terms, it will be closer to 1.5 again. And then if you add a large number of terms, it will then go closer to 1.5. So our answer here really means that the series converges to 1.5. It's going closer and closer to 1.5 as we add more and more terms in our series. Really, really fun stuff. I hope you enjoyed this question, and I'll see you next on the next series of questions. We'll move now to questions that look at functions. I'm very excited about that part of the question paper.